Hi everyone, this is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Yeah, today we will be discussing about FIR with the windowing techniques. Yeah, introductions to windowing method, windowing, types of windows, advantages and disadvantages of the windowing technique, steps of steps for solving the problems using the windowing method, uh, examples using rectangular window, examples using Hamming window. We like to discuss this all contents. Okay, so windowing method to design finite impulse response filter. Here, if we have made it is this for in this digital signal processing course for implementing this all digital filter. This is the major role. You might have had a few moments where you had we have thought of the jumping out of the windows. Okay, but bear with me and leave this windowing technique for finite impulse response filter. Digital filter, you can see the windowing method for designing FIR filters. So trust me, it is not a complicated as it is seems. Okay, now coming to the introduction to the windowing method, we know that aware of this all windows like Hamming window, Kaiser window, and Sabichu, Dal Shabichu window, and Luckman, and so on. This is the popular windows. So here it would seem straightforward to think that to obtain the casual finite impulse response filters, we can just truncate it, the infinite Fourier series of the non-causal infinite impulse response filter. Okay. However, in practice, the abrupt nature of the truncation causes oscillations to show up on the passband and the stop band of the filtered response. Okay, in this also known as Gibbs phenomenon that we had previously discussed from the beginning of this digital signal processing and so on. So the windowing technique in which the windowing function is multiplied with the desired frequency response. It's like that FIR filter, we can just truncate it in the infinite Fourier series of the non-causal infinite impulse response. The abrupt nature of the truncation causes oscillations to show up the passband or stop band of the filter responses. With this, it helps minimize the effects of these oscillations, giving us a more desirable output from the truncation of the IARE filter. Okay, infinite impulse response. Okay, but here we are going to use that finite impulse response for windowing technique. Okay, for this windowing, you know that all everybody knows that all windowing, but how do you determine the frequency range to ensure your design and effective filter? For this is where the windowing technique comes in. What you call visualize the sending and infinite functions into a window to get back a finite part of it that enables us to analyze it with the more easy. Okay, that is essential what we are trying to achieve with the windowing method. So based on that, after that, we try to design our FIR filter, finite impulse response digital filters. Okay, this is the essential what we are trying to achieve this windowing method. So breaking this down, first we have to choose a proper what you call a frequency selective IAR filter. Okay, after that, this filter usually has a non-causal. Okay, that means has both negative and positive points. So and the infinite duration impulse responses. Okay, with this, so the specification of the frequency response is usually given in the what you call form of Here is the waveform of the frequency response. Okay, so this frequency response should be converted to a unit sample response using the Fourier transform relation. We know that we will ready to verify this one. It is nothing but we'll try to verify the graph of either it is infinite function or not. Okay, I would try to justify that this frequency response should be converted to unit sample response using the what you call Fourier transform relation. Okay, and so on. Here, n versus SD of n. This is the Fourier transform relation with this. Okay, so in the mathematical analysis, SD of omega is equal to the summation n is equal to the summation what do you call here it is the summation. Okay, where n is equal to 0 to infinity. Okay, SD of n into e power minus j omega n. Okay, go on. Is to concentrate on this what the small n value and SD value and so on. For here SD of n is equal to here where we know that SD of n SD of where here SD of n where SD of n is equal to what you call we know that are 2 1 by 2 pi integral minus pi to plus pi. Okay, with this SD H capital HD of omega into what you call e power j omega n with the d omega. With this, you have to analyze this SD where SD of omega. This SD of omega, we know that what you call the summation where it is where small n is equal to 0 to infinity with a small hd of n, okay, into e power minus j omega n. So with this now we want to send this waveform through a window, basically truncate the waveform so that we obtain a casual and linear phase finite impulse response filter. It is opposite of what we had before, like a IARE filter, which basically means finite and probably positive. Okay, so with this, the filter is truncated to a particular length. This length is also known as the window length. Okay, so using this particular window length, uh, we easily can analyze that we a casual and linear phase FIR filter. Okay, uh, which is so the filter is what we call truncated to a particular length. This length is also known as the window length. Okay, with this, let's say it is the truncated at the point n. Okay, so now which means the finite impulse response filter length would be what you call capital M is equal to, which you can analyze, n plus 1. Let rectangular window be W of n, which is given as what you call W of n is equal to 1, where n is ready to substitute, up to what you call where n is equal to initially 0, 1, 2, 3, 4, and so on according to the order of the filter, and we can consider m minus 1. If it is, we know that since here capital N is equal to what you call order of the filter is m minus 1. With this, okay, here omega n equal to 0, otherwise what do you call is where n versus omega n n is increases and omega n is how it is reflected. Okay, waveform of the w of n of now. So now we are combining these two waveforms and w of n to obtain h of n. The unit sample response of the finite impulse response filter. Okay, for n is equal to 0, 1, 2, 3 and so on up to m minus 1, 0 otherwise. Okay, like this. Hence, this graph of h of n would look like this, which is basically the convolution of the and what you call w of n. So with this, now we are coming to the two waveforms and w of n and obtained h of n. The unit sample response of the finite impulse response filter for n is equal to 0, 2, 3 and so on. Like this, it is response after being the filter. Okay, like this we are to verify. Hence, the graph of h of n. Okay, it looks like this, which is basically the convolution of an w of n. So the response after being the filtered. Okay, so for a bit of perspective, let us take the equation of the linear phase finite impulse response filter where the order of the m is even. Okay, if okay, so where is the real magnitude function or not, we will try to verify. So after that, we are going to start off by minimizing the mean square error between the actual filter and what you call desired filter. So with this, the coefficient of the actual filter is represented by what you call h of k. Okay, so where the represents the desired response and what you call represents the actual response. So like for a bit of perspective, the equation of the linear phase finite impulse response filter where the order of the m is even. Like here that h into e power, here it is h into where h is equal to that summation k equal to 0 to m h of k. Okay, and into e power minus j k omega is also equal to what you call e power minus j omega m by 2 a into omega. Okay, with this, what do you call h of n? Okay, that h of k is equal to h of k power of 1 by 2 pi integral minus infinity minus integral minus pi to plus pi sd into e power j omega minus h into e power j omega square t omega. Okay, so for a bit of perspective, let us take the equation of the linear phase of FIR filter where the order is m is even. Okay, like this, we are using this mathematical notation where omega is the real magnitude of the function. Okay, we are going to start off by minimizing the mean square error between actual filter and distant filter. The coefficient of the actual filter is represented by h of k. We know that. So for this case here, h of k, okay, h of k, that is the minimum power 1 by 2 pi integral minus pi to plus pi h d e power j omega minus h into e power j omega square, okay, d omega. Okay, so with this, where HD, what do you call HD into e power j omega, it is represents represents the desired response, and hn2 e power j omega is represents the actual response. Actual, yeah, actual response. Here it is. Represent these are the desired response, dr. Okay, the desired filter is also a linear phase finite impulse response filter with the same group delay. Okay, so let us this equation be represented. Now it is the same group, or already we have discussed this phase, what is the group delay, with the same group delay. Okay, so now here it is. The desired filter is also a linear phase FIR filter. Linear phase finite impulse response filters with the same group delay. Let this equation represents this one, where the mean square error is represented equation number 1. Okay, so where a of k equal to h of k plus m by 2, this represents the shift of the left and apply the DFT, DTFT, discrete time Fourier transform to a of k. We will obtain a of omega. Okay, so this the Parseval's theorem. So already we have observed that all properties on see that properties of DFT. From that properties state that the integral of the magnitude square in the frequency domain is equal to the sum of the magnitude square the time domain. Hence the equation 1. This equation 1 can also represented can also be written as a a k summation k equal to minus infinity plus infinity ad of k minus a of k square. It is represent the equation number 2, where ak is equal to, okay, that ak is equal is a non-zero for the interval minus m by 2 less than or equal to k less than or equal to m by 2. Okay, so expanding this equation to, here it is already. Observe the equation number 2. So we're going to expand this one. Of that we are ready to analyze our desirability. Okay. Excuse me. Yeah, expanding this equation 2, we get what do you call this? That's a k. It's a minimum summation k equal to minus infinity to plus infinity. ad of k minus ak of k is equal to summation k equal to minus m by 2 to plus m by 2. Adk of k minus ak of ak square plus summation k equal to minus infinity to minus m by 2 minus 1 ad into k whole square. We have to choose ak accordingly so that the first term becomes 0. Okay, to satisfy that, let's ak is equal to, what do you call, ad of k of m by minus m by 2 less than or equal to k less than or equal to m by 2. This is actually equivalent to multiplying the infinite response with the windowing function. Okay, windowing function a of k is equal to ad of k into omega of k. This is the same as, what do you call, a of omega is equal to ad of omega into e power j omega. Okay, like this, w into e power j omega. Here is a graphical representation of the, what you call, convolution happening in the above equation. Okay, the discrete Fourier transform, the DTFT, discrete time Fourier transform of a ad of k, which is ad of omega. Okay, like this, the discrete time Fourier transform of ad of k, which is ad of omega, So omega versus AD of omega. So ready to verify that the response is magnitude function of the desired filter. This is the rectangular window function is shown in, okay, like this. So rectangular window function is shown in below here. K versus W of K. This is related to the graph of window function. Okay. So taking the discrete Fourier transform of the windowing function, we get the graph of what do you call h into e power j omega. Okay, here that omega versus w of e omega, the width is 4 pi by what do you call emergent graph of discrete time Fourier transform of w of k function. Okay, this graph by the main lobe, here it is, these are all your main lobe. So number of side lobes are observed here. Okay, so this the graph is by the main lobe having width is, or that width here, main lobe width is 4 pi by m plus 1. This is the main lobe width up to here, here to here. This is the width of main lobe. Okay, so the first peak side of the lobe goes down to what you call minus 13 decibel related to the main lobe. So the convolution of the windowing function and the desired filter magnitude response will give up the graph is graphically it is available after using this graph of discrete time Fourier transform of W of k function. So how it is appeared like this, graph of magnitude of A of omega, omega versus A of omega. So here as you can see from this graph, there are many isolations. Okay, as per this diagram, so many isolations and ripples present in the stop band and the pass band. Okay, stop band and the pass band. The main lobe of the graph, okay, is what you call W of e power j omega determine the transition bandwidth, and the width of the side lobes determine the pass band and the stop band ripples. This is the analyzing the graph of magnitude of omega for this level. Okay, this the convolution of the windowing function and the desired filter magnitude response will give us this one. Okay, now as we can see from the graph, there are many isolations from this diagram. Okay, so ripples represent ripples presents in the stop band and the pass band. So the main lobe of the graph of the determines the transition bandwidth, and the width of the side lobes determine the pass band and stop band ripples will be observed here. Okay, these ripples are not acceptable for a filter of the quality. So we want to avoid this all. If we want to use that all partially or for normal application purpose, we can use. But normally, if it is once you are entering that practical response, practical aspects, these ripples are not acceptable for a filter of the quality. Okay, so with this, too many ripples on the pass band and stop band will not let a filter do its function well enough. Okay, so typically other windows are used to trade the main lobe with like you can see the transition band, the side lobe widths are ripples. Like this we are trying to analyze. This is the interpretation level of the previous output response. This is the graph we try to decide the factors. Okay, these ripples are not acceptable for the filter of the quality, but people are expecting real-time aspect. The filter of the quality is required. Okay, this is the types of windows. What do you call type of window and windowing function and shape of the windowing function, width of the lobes of the frequency response. If you want to consider these are rectangular window, windowing function is this one, and shape of the window is looks like this. This is the window, and here is a width of the lobes of the frequency response is main lobe width is 4 pi by m plus 1. Height of the side lobe is minus 13 decibels. This is a rectangular window. Coming to this Bartlett triangular window, so where this is the windowing function, this is the shape of the windowing function, and the main lobes. That main lobe width is 8 pi by m. But here it is, main lobe width is 4 pi by m plus 1. Height of the side lobes are minus 25 decibels in Bartlett. Here it is rectangular window minus 13 decibels. Okay, with this right analyze the types of windows. So as we see this what do you call this particular graph, types of the windows. So after that we go for here rectangular window, Bartlett, it is our triangular window. We have seen that easily right to compare the windowing function, shape of the windowing function, or width of the lobes of the frequency responses. Next, Hanning window and Hamming and Blockman windows. It is window function. That window function is here. Window shape with the main lobe is Hamming window main lobe is what you call width 8 pi by m. Height of the slope is side lobe is minus 31 decibels. Okay. Coming to the Hamming window, the main lobe is 8 pi by what you call m. I think so. This Hamming the main lobe width is same. Height is somewhat is compared to Hamming is increases here minus what you call 41 decibels. Okay. Coming to the Blackman window, here is main lobe is 12 pi by m, and the height of the side lobes are minus 57 decibels. Okay, like this, we like to compare this all windows. After that, we like to choose. This is a desirable window, required window. After using this all windows, we will expect that all quality of the filter. Next, Kaiser window. Okay, now design of the FIR filter by windowing. FIR filters are designed based on the directly approximately the desired frequency response of the DTS, discrete time system. Okay, so most techniques for the approximating the magnitude response of the finite impulse response system assume a linear phase constraint. Okay, so the window method, an ideal desired frequency response is this one, that is SD, where what do you call that? An ideal desired frequency response is followed by SD power j omega is equal to the summation where n is equal to minus infinity to plus infinity SD of n with SD of n into e power minus j omega n. Okay, if you are in the low pass, what do you call, if it is low pass filter with this, okay, SD the HLP e power j omega is equal to 1 comma mod window less than omega c, 0 omega less than or equal to mod omega less than pi. So like this pi versus h into e power j omega. So is ready to analyze that windowing method, an ideal desired frequency response case. Okay, so with this, many idealized systems are piecewise constant frequency response with discontinuities at the boundaries. So as a result, these systems have impulse response that are non-causal and infinitely long. Like this. Okay, so window method, the most straightforward approach to obtain the casual finite impulse response approximation is to truncated ideal impulse response. For this, this all we know. Okay, this h of n is equal to sd of n and w of n. Where in this case, graphically, right, to verify this one, h and t power j omega is equal to 1 by 2 pi integral minus pi to plus 5 h and sd into e power j omega w of e power j omega of omega minus theta into d theta. Okay, now windowing in the frequency domain, windowed frequency response h and t power j omega is equal to, you know that, 1 by 2 pi integral minus pi to plus pi sd into e power j omega w e power j omega minus theta into d theta. The windowed version is measured version of the desired response. Like this graphically, right, to verify. Now, if w of n is equal to 1 minus infinity less than or equal to n less than or equal to infinity, so that window will be displayed like this with the help of this mathematical notation. And I will try to analyze that graphically. So now come to the choice of the window. It is for w of n is a short as possible in duration. This minimizes the computation in the implementation of the filter. We can consider that w of n is equal to 1, 0 less than or equal to n, small n less than or equal to capital M, 0 otherwise. Okay, so with this w of e power j omega approximates an impulse. Okay, w of e power j omega is equal to summation n is equal to minus infinity to plus infinity w of n into e power minus j omega n. It's also equal to the summation n is equal to 0 to m e power minus j omega n. Okay, like this, where w of e power j omega is equal to 1 minus, here 1 minus e power minus j omega of m plus 1 by 1 minus e power j omega is equal to e power j omega m by 2 into sine of w of m plus 1 by 2 sine of w by 2. So we will expect the term response here. Okay, like that pi versus that m plus 1. Okay, finally that mod w of e power j omega. Okay, window method. If we w of n is chosen so that w of e power j omega n is concentrated in a narrow band of the frequencies around maybe equal to 0. Then h and e power j omega would looks like sd of e power j omega, except where sd of e power j omega changes very abruptly. Okay, like this. We need to verify. Next, rectangular window. You have seen this one. Rectangular window with will oscillates at discontinuities. Okay, these oscillations occur more rapidly but do not decrease in magnitude as m increases. Rectangular window. By tapering this window smoothly to 0 at each end, the height of the side lobes, okay, the height of the side lobes, okay, uh, can be diminished with this. The expensive, yeah, the expensive is wider main lobe and thus a wider transition at the discontinuities, like this, right, to verify. Okay, now we are to design a FIR filter with the help of what do you call length m is a LTS system with the following the difference equation. Yeah, sometimes we are right to verify that an LTS system is causal if so we have seen it is observed. Semi-FIR filter, symmetric and anti-symmetric FIR filter linear phase also we have seen. Okay, yeah. So this different types of windows already we have analyzed: rectangular, hamming, and hamming. Knock and Bartlett, or we can consider the triangular window, Kaiser windows. So in depth of this rectangular window, this is the simplest window function but provides the worst performance from the viewed of the stop band attenuation. Okay, the width of the main lobe is 4 pi by n, and if you are in the Bartlett window is also a triangular window. The width of the main lobe is 8 pi by m, you know that all. Come to the Hanning window. Yeah, this is a raised cosine window function is given by omega of n. The width of the main lobe is 8 pi by m, already we have seen. Okay, now here the FIR filter design windowing technique. If you are in the Hamming window, this is a modified version of the raised cosine window. You can consider this all mathematical notation here, using this all formula. W of omega approximately what do you call 0.54 WR of omega plus 0.23 WR of omega minus 2 pi by m. Like this, the width of the main lobe is 8 pi by m. Like this, Hamming window, Blackman window, and Kaiser window. So with this, the windowing function is already we have seen this all windowing function. With here the window and windows and its functions. If it is rectangular window, that window function is ready to remember this all is equal to 1 for 0 less than or equal to m less than or equal to m minus 1. Okay, 0 otherwise. Come to the Bartlett or triangular window, omega t of n is equal to 1 minus 2 pi n minus m minus 1 by 2. Like here, mod this one 2 into n minus m minus 1 by 2 by m minus 1. Yeah, coming to this Hamming window, what purpose this all? We want to design this all what you call digital finite impulse response filters. We are in the different windows. This is the popular windows. You have to remember this all windowing function of that writing the piece of code in what you call in MATLAB, right, to verify that all your response. Okay, Hamming W of n is equal to 0.54 minus 0.46 cos of 2 pi n by n minus 1. So here Hamming window 0.5 minus 0.5 cos of 2 pi n by n minus 1. Okay, coming to the Blackman window, here 0.42 minus 0.5 cos of 2 pi n by n minus 1, 0.08 cos 4 pi n small n by capital N minus 1. So these are the related windows. So if you want to design this all window aspects, you have to remember this all Gibbs phenomenon. The magnitude of the frequency response h of omega is as shown in figure. So large oscillations or ripple occur near the band edge of the filter. The oscillations increases in frequency as m increases. If it is m increases, what we call the oscillations also increases. Oscillations increases in frequency as m increases, but they do not diminish this amplitude. Okay, so these large oscillations are due to the result of the large side lobes existing in the frequency characteristic W of omega of the rectangular window. Okay, and the truncation of the Fourier series is known to introduce the ripple in the frequency response characteristics. It is followed by what you call h of omega due to the non-uniform converge of the Fourier series at a discontinuities. Okay, so the oscillatory behavior near the band edge of the filter is called the Gibbs phenomenon. Okay, so to evaluate this, the presence of the large oscillations, both the passband and the stopband window function is used that contains the taper and decays towards zero gradually. This is the greatness of analyzing the Gibbs phenomenon. Okay, so there is a Flex 4 digital filter analyze options. This discover this latest design technique for the easiest operation. Flex Pro analysis wizard merges the steps of filter design, filtering, and presentation into the simple sequential process using the real-time two-dimensional and three-dimensional graphs. FlexPro offers you immediate visual feedback whenever any change is made to the filter specification for designing your digital filter. Okay, with this enhanced IAR filter. Okay, IAR filters including internal feedback, like here it is the recursive filter, and it is the recursive filter IAR, and provides a high degree of the stiffness with a short filter length, making it is possible to design. It is possible to design low pass, high pass, band stop filter. Okay, with this FIR filter design. So FIR filter avoid the feedback and are therefore always stable. Compare this IR and FIR. FlexPro offers you two procedures for calculating the phase linear filters. Okay, phase linear filters. Phase linear filter with the minimum filter length. Minimum filter length. What are the features? So, FIR filter design using the windowing method. Use the Kaiser or Ceviche window to specify the filter's length, attenuation, and transition width more precisely. You only have to provide two parameters. The third parameter is calculated automatically. This is the feature for designing what you call a FIR filter using the windowing method. Like this, to open that all MATLAB. So verify here, the filter signal is selected. Okay, using this all, there is a possibility for designing all smooth filter and CFS filter. After that, we try to analyze the wizard, like step to analyze the types. Okay, so many filters are available. What you call filter type and results ready to verify and the filter characteristics. Okay, so here I am selecting the Ceviche. Okay, or we can try to select the Butterworth or the Bezels or maybe inverse Ceviche and so on. So finally we try to decide that all. So for designing what you call IAR, what you call FIR digital filter for analyzing windowing method. Finally, using these all features, you can analyze that which one is the best in features. Previously, we are using only what you call rectangular window, okay, and what do you call Blackman window. We have seen in future also we are to design using the Kaiser or Ceviche windows to specify the filter's length, attenuation, and transition width more precisely. So you only have to provide the two parameters. The third parameter is calculated. Finite impulse response filter design using the windowing method. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.